Hello and welcome to Weapons of Math Instruction. This is our fourth video in celebration of Pi Day, which was March 14th. I released the other three videos last week, and I wanted to get the fourth and fifth videos out last week as well, but I was traveling and I couldn't get them done before my trip, so I'm doing them now just to get them on the record. I'm going to present a proof that pi is irrational that was given by Ivan Niven. I presented this proof in video 5 of the Pi Day 2021 series, but that video was kind of long. It was about 20 minutes. And I spent the first 7 minutes explaining what the integers, the rational numbers, the real numbers, and the irrational numbers are. This time, I want to streamline things and just present the proof. In case you want to see that background information that I presented in the beginning of last year's video, I'll post a link to that video in the description. So here's just a little rundown of some basic facts. First, pi is a real number, but it's not rational. So that means that pi can't be written in the form p over q, where p and q are integers. In other words, pi can't be written as the ratio of two integers, so it's irrational. So like I said, I'm going to present the proof by Ivan Niven that was given in his paper, A Simple Proof That Pi is Irrational, which he wrote in 1946 and was published in 1947. And Niven's proof is a proof by contradiction, which is a neat piece of reasoning in mathematics. Proof by contradiction is also known as indirect proof. What does that entail? You assume the negation of the proposition P that you want to prove. So in this proof, the proposition P is that pi is not a member of the rationals. And so the negation, not P, is that pi is a member of the rationals. And what we do is we derive a contradiction from not P. And since contradictions are not logically possible, we conclude that not P must be false, and therefore P is true. And this method of proof is useful when direct proof is difficult or even impossible. And here's Niven's paper in which he presents his proof. And sure enough, it looks pretty simple as the title advertises. I mean, look at it. It all fits on one side of one page. However, Niven leaves out many steps. And in this video, I'm going to unpack all those details. So in the paper, Niven assumes that there exist two positive integers a and b such that pi equals a over b. That is, he assumes that pi is rational. Then he defines two polynomial functions, little f of x and capital F of x, each of which we'll discuss below. And they each contain an arbitrary positive integer n. So the first function, little f of x, is x to the n times a minus bx to the n over n factorial. So this is a polynomial function of degree 2n. You get n powers of x from here, and you get n powers of x from here. The second function, capital F of x, is also a polynomial function, and it's defined in terms of the derivatives of little f. These superscripted numbers in parentheses are the orders of the derivatives. So here's the second derivative of f, here's the fourth derivative, and we go all down the line here until we get to the 2nth derivative, which is the highest order non-zero derivative of f. Now we're going to lay down some groundwork before we start the main argument of the proof, because I don't want the reasoning of the proof to be obscured with a bunch of messy details. So I'm going to rewrite f using the binomial theorem like this. Then I'll rearrange the factors of the coefficient of x to the j power in these brackets here. And this expression is kind of a mess, but fortunately we don't care about the details. The only thing that matters for the proof is that this entire coefficient in brackets here is an integer. So I'm just going to rename this whole mess. I'm going to call it c sub j. And this is fine, because Niven's proof largely hinges on the coefficients of the function capital F being integers, and that's all we really care about here. And in this final step, I brought x to the n over n factorial inside the sum. Now, since capital F is expressed in terms of arbitrary derivatives of little f, I'm going to want an expression for the kth derivative of f. And there are two cases to consider. First, there's the case where 0 is less than or equal to k, which is less than n. So right here, I'm about to let the kth derivative operator act on the function little f. And when you differentiate a power of x, the exponent multiplies the coefficient and you reduce the power of x by 1. But this happens k times. So we've got this collection of k factors right here, from j plus n to j plus n minus k plus 1. And here, the power of x has been reduced by k. And again, it looks like we have an awful mess here. But this string of factors from Cj all the way down to this guy here, they're all integers. So their product is an integer. So I'll just rename it. I'll call it d sub j, which is an integer. And so the kth derivative cleans up like this. Now, the second case is where n is less than or equal to k, which is less than or equal to 2n. So once again, I'll let the kth derivative operator act on f. And this time, k is large enough so that some of the derivatives of these x's here are going to be 0. So to get rid of those 0 terms, I'll start the sum at k minus n instead of 0. Other than that, the kth derivative looks the same as it did in case 1. And once again, we'll group all these factors together and call it d sub j, and we'll clean up the kth derivative like this. Now this time, the kth derivative is going to have a constant term, specifically when j equals k minus n. And that constant term is k factorial over n factorial. And so I've pulled that out right here, and I've grouped the rest of the terms together in this sum, which now starts at k minus n plus 1. Okay, that sets the table. Now I'm going to prove a series of 4 lemmas. What's a lemma? It's an intermediate result that needs to be proven on the way to the main result, which is called a theorem. Lemmas help streamline the proofs of theorems. So lemma 1 is that capital F of 0 is an integer. So we're going to show this by examining the kth derivative of little f at 0. And as we saw, there are 2 cases to consider. One where k sits between 0 and n, and one where k sits between n and 2n. Okay, case 1. K is between 0 and n. So here I plugged 0 into the kth derivative of little f, and that 0 is right here. And you'll notice that every term in this sum is 0. So the sum itself is 0, and 0 is an integer. And case 2 is where k sits between n and 2n. And in this case, if I plug 0 into the kth derivative of little f, something similar happens. All these terms go to 0, but I'm left with this constant term over here. So this equals k factorial over n factorial. And that's an integer because k is at least as big as n. So, since the kth derivative of little f at 0 is an integer for all possible k, then it follows that capital F of 0 is an integer as well. So that proves lemma 1. Lemma 2. Capital F of pi is an integer. Now remember, we're doing a proof by contradiction here. So pi is the rational number a over b by assumption. And the contradiction that's going to happen at the end of the proof will be due to this assumption. Okay, let's prove this lemma. We'll do it by examining f of pi minus x, which by assumption is f of a over b minus x. It turns out that little f has a slick little transformation property that we can exploit. Okay, so here's f of pi minus x. So I've plugged in a over b minus x for x in the first factor here, and in the second factor here. Alright, in this step, I took the first factor and combined the 2 terms with a common denominator to get this guy. In the second factor, I distribute this minus b over these 2 terms, and I collect like terms to get bx to the n. And notice I have n powers of b right here, and I have n powers of b in this denominator right here, and those are going to cancel out, and I will get a minus bx to the n times x to the n over n factorial, but that's exactly f of x. Ta-da! Okay, we're going to differentiate little f k times. So by the chain rule, the kth derivative of little f at x is negative 1 to the k times the kth derivative of little f at pi minus x. So we'll plug in x equals pi. So the kth derivative of little f at pi is negative 1 to the k times the kth derivative of little f at 0. But we just showed in lemma 1 that the kth derivative of little f at 0 is an integer. So if you take this integer and multiply it by this integer, you're going to get an integer. So this guy here is an integer. So, since the kth derivative of little f at pi is an integer for all possible k, it follows that capital F of pi is an integer as well. And that proves lemma 2. Alright, lemma 3. Capital F double prime of x plus capital F of x equals little f of x. The proof is straightforward. We start by writing down capital F of x, and we take the second derivative. So all the derivatives that you see here get pushed up by 2. We don't bother with the derivative of order 2n plus 2 because that's 0. Remember, little f of x is a polynomial function of degree 2n. Now notice something. If we add these 2 expressions together, all these terms are going to cancel each other out, leaving only f of x. And that proves lemma 3. Lemma 4. The derivative of capital F prime of x sine of x minus capital F of x cosine of x equals little f of x sine x. So the proof is a straightforward application of the product rule from calculus. So taking the derivative of this first product here, I get capital F double prime of x times the sine of x plus capital F prime of x times the cosine of x. And taking the derivative of this second product here, I get capital F of x sine of x minus capital F prime of x cosine of x. But notice the second and fourth terms are going to cancel out. So when I add those together, I just get the first and third terms, like so. But by lemma 3, that equals little f of x sine of x. So that proves lemma 4. And at last, we're ready for Niven's main argument. So in his paper, Niven considers the integral from 0 to pi of little f of x sine of x dx. Now by lemma 4, this integrand is equal to the derivative with respect to x of capital F prime of x sine x minus capital F of x cosine x. So now we're integrating a derivative, which is easy. We just get what's in parentheses. So here I've applied the fundamental theorem of calculus. And so right here you see I've evaluated the quantity in parentheses at pi. Here I've evaluated it at 0, and I subtract. And I simplify to get capital F of pi plus capital F of 0. Now, by lemmas 1 and 2, these are both integers, and so their sum is as well. So this integral at the top here is integer valued. But check this out. In this integral, x is between 0 and pi. That means that a minus bx is between 0 and a. Multiplying these two inequalities together, I get that x times a minus bx sits between 0 and pi times a. Now, in case it's not clear what I'm doing, I'm trying to build the integrand in the middle member of this inequality so that I can place bounds on it. So here, I raise all three members of the inequality to the power of n. And here I divide by n factorial. Now I've got little f of x in the middle member, like so. And since on the interval from 0 to pi, sine of x is between 0 and 1, I can multiply the middle member of this inequality by sine of x without changing the bounds. So, our integral must satisfy this inequality here. On the left, we see that the integral has to be positive. And on the right, we see that it's bounded by the upper bound of the integrand times pi, which is the width of the interval of integration. So not only is this integral an integer, it's a positive integer. But as n grows arbitrarily large, the upper bound on the integral grows arbitrarily small. This is because the factorial in the denominator grows much faster than the exponential in the numerator. But since the integral is integer valued, this is a contradiction. There is no arbitrarily small positive integer. The smallest positive integer is 1. So our assumption that pi is rational must be wrong, because the rest of the proof is solid. Therefore, pi is irrational. And that completes the proof. Thanks for watching, and tune in for the next video. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.